My name is Clay McKell. I am a lecturer here in the EE department at Cal Poly. This is EE302. We're going to be talking about classical control systems. We're going to be working a lot with Laplace transforms, block diagrams, and system metrics. So we're going to pick up where you left off in EE228 and just go wild. So this class is called Classical Control Systems, and we are going to be learning about what a control system is, how you measure one against the other, see which one is better, and the design choices you can make to improve the performance of basically linear time invariant systems. So you remember the LTI abbreviation from 228. That's all we're going to be talking about this quarter. So the first unit in the class is how do you model a system? Once you have a system model, then you can start talking about how would you modify it or what would you add to it to make it better. And that sentence pretty much encapsulates the course, and we're going to unpack that over the next 9 weeks. All right, this is a scary slide. The idea is there's got to be some kind of process, and nominally it's a linear process. You start in step 1, you go through to step 6, sure, but I've tried to indicate that sometimes you got to backtrack with these arrows heading back. So this is the idea that if you're going to model a system, you first got to, in step 1, you've got to determine what the physical system is. So what are you talking about? In the following slides, we're going to be following a couple examples. The first is everyone learns this in their first controls class, is cruise control in your car. That's an example of a control system. We're gonna use that model as an example as a way to kind of unpack this 6-step process, if you will. But I want to run you through the steps here, and I mostly want to talk to you about step 2, a functional block diagram, versus step 4, what I'm going to call a Laplace block diagram. And a functional block diagram is super rough. It's something that you might draw on the back of an envelope. It is what are the major components of the system and who talks to whom and what do they say. In an electrical system, this might be your functional block diagram. You would have a block that takes AC power and converts it to DC. So your power unit would be one functional block. The next block would be, if I was designing I don't know, a personal computer, a PC, I would then take that DC power and say, okay, some of it has to go to the CPU, some of it has to go to the GPU, some of it has to go and drive auxiliaries, and those would be 3 blocks. Like, there's way more to a computer than 3 or 4 blocks, but at the very outset here, we want to make sure that we've got all the main players on the page and roughly who talks to whom. Now that functional block diagram in the step 3 that I have here, you'd then transform that into a schematic. So this is more like in that AC to DC power converter, what are the circuit components involved? Where are you putting the resistors? Where are you putting the diodes? Where are you putting the op amps? How are they all connected? So a schematic can mean a circuit diagram, but a schematic is also a free body diagram. Say if you're going to use a mechanical system, where are the forces? Where are the torques? So I'm using this term schematic to kind of generalize what you and I think of when we think of a circuit diagram, because other disciplines are going to have different concepts or different use cases for technical drawings with components that all have relationships. That's kind of what a circuit diagram is for us, but that's also what a free body diagram is to the mechanical engineers. So then you would use that schematic circuit diagram, if you like, and transform that into a block diagram. What are all the small components and how do they all talk to each other? What is the differential equation that relates inputs to outputs? Once you have that differential equation, then you can start talking about the Laplace transfer functions of the different components of the schematic. You're likely going to have a bunch of different subsystems in that step 4 Laplace block diagram. Step 5 is take those multiple Laplace blocks and condense them as much as you can until you get, say, nominally, a single transfer function from input to output. Once you have that transfer function, which is basically what we started with in 228, right? A lot of the questions in 228 were, here's a transfer function, where are its poles, what is its impulse response, yada, yada. But basically steps 1 through 5 are the lead up to that kind of question in 228, or that kind of problem, which I've kind of encapsulated here in step 6, which is take that one transfer function and then analyze that. Okay, so any questions so far?
I assume this isn't the proper place to ask about a particular homework problem, correct? Well, I was looking at the mechanical system with the pendulum, and I was like, all right, I'm thinking about doing an FBD before I get to drawing a block diagram.
I mean, that's kind of what I just said, right?
Oh, okay, yeah.
Yeah, so give me a couple of minutes to go through the examples, and hopefully I'll answer some of your questions there. Okay, so in step 1, so I'm going to take those steps and I'm going to kind of lay them out onto this cruise control problem. So to remind you, step 1 was determine the physical systems and the specs from the requirements. So in the cruise control example, the physical system, we're only going to make a cruise control for a single model car. You could talk about designing a cruise control that could be plopped into multiple cars, but let's keep it simple. Once you specify the make and the model of the car that you want to build the cruise control for, that fixes a bunch of physical properties, kind of like how much mass are we talking about moving? What's the engine size? What are the engine capabilities? What's the gear ratio and what kind of tires is it using, that kind of deal. So I hope you see that this step, it sounds kind of trivial, but if you don't do this step, you open yourself up to what's called specification creep. So what I'm kind of, in a normal class, I would ask you to kind of spitball what you'd like the requirements for a cruise control to be. Because it's one of these systems that everyone's used it, or I like to assume that everyone's used it, or at least heard of it. But I think I'm going to go ahead and fill in the blanks for you. So by and large, a cruise control system has to maintain a set speed in the car. But also you'd like the driver to be able to change that speed. So as far as I can tell, those are the requirements, like the kind of end-to-end requirements of a cruise control system. You could get a little bit more nitty-gritty and say, well, let's maintain a speed somewhere between 20 and 80 miles an hour. Okay, most cruise controls will work in that range. But let's give ourselves the benefit of the doubt and here have a broad set of requirements. Just maintain some speed, and when the driver changes the speed, the car has to change its speed to match that speed. Okay, so those are what I'm calling the requirements. What is a specification versus what is a requirement? Well, a specification is much more quantifiable, right? A requirement might be maintain a set speed, whereas a specification might be something like the following. The car needs to keep its instantaneous speed bounded for any given input. All right, that seems like a reasonable request, that if I set the speed to be 65 miles an hour, the car doesn't proceed to an unbounded speed and then come back down to get there. Specification number 2 is eventually achieve any set speed exactly. Okay, so this is a bit of a reach. Do you as the driver really care if you're going 65 miles an hour or 64.9 miles an hour? I mean, perhaps there are some applications where you need to be exact, you know, to the nth decimal place exact. I think cruising on the highway isn't actually one of those cases. So I want to point that out, that this specification number 2 didn't have to be that way. It could have been a little looser. There could have been some tolerance built in there. And then also note the parenthetical statement that we don't drive on purely flat roads. I guess if you are watching this from Kansas, then you do. But in general, we have to be able to maintain a speed in the presence of uphills, downhills, crosswinds, gusty winds, these kinds of things. And then specification number 3 has to do with transitioning from one set speed to another. So if I go from a 65 zone to a 70 mile an hour zone, I'd like the car to match the new speed within T1 seconds, but not within T0 seconds. Can you imagine why that might be? I want to get there reasonably quickly, but I don't want to be accelerated into the back of my seat so it becomes uncomfortable. Okay, so I have enumerated these specifications in three items here. Night mode. Since we're on the tablet, I think I'm just going to carry on in the dark. Is that all right? Yeah, everyone's in the dark here, metaphorically. So the specification I have listed as number 1 is what's called a stability requirement. Right? This has the language of bounded input, bounded output stability that you learned about in 228. So what specification number 1 would be classified as a stability requirement, or a stability spec, I should say. Specification number 2 is what we're going to call a steady state metric. So this is the idea that I don't care how long it takes to get to a certain place, but in steady state, I need the system to perform blah. And that is in opposition to specification number 3, which I would call a transient requirement. So these are the 3 main legs that hold up any control system. You need to, in general, ensure that the system is stable. You need to ensure that it meets the steady state requirements, and you need to ensure that it meets the transient requirements. These 3 legs of the table will roughly correspond to 3 of the units that we're going to cover in this course. Questions so far? All right. So what would a functional block diagram look like for the car? Well, the input to the system is going to come from the driver. So the driver is going to set the desired speed. And that is a signal, right? That's a desired quantity. It's not a system. And the other relevant quantity, or the output of this entire system, is going to be the actual speed of the car. So, big old blank space in the middle there to fill in the important bits. So, what follows is basically the essence of a control system. I want the car to go 65 miles an hour, but that's not the input that I tell the engine. Okay, so there's a bit of anthropomorphizing going on here. But the idea is we don't command the system with what we want. We command the system based on the error. So the output of this, what I would call a summing junction, is what I'm going to call the error in the speed. So let's take a second to think about that. This summing junction, this little circle here, is a system. Let's not confuse it. It's a system that takes 2 inputs, assigns one a positive sign, assigns the other a negative sign, and the output is the sum of those 2 inputs, summing junction. Here we're looking at what do I want, the driver's set speed, minus what do I have, the actual speed of the car. If that quantity, just in very broad strokes, if that quantity is positive, then the car's going too slow, which means we need to tell the engine do something positive in very broad strokes. If the error signal is negative or too low, that means the actual speed exceeds the desired speed and we're going too fast. That means the engine now has to do negative work or take in speed or whatever you like. So the next block is in the functional block diagram. You could think about some kind of logic that you'd like to apply to that signal. If it's been X for time T, then do Y, or something like that. You could also think about using some kind of intelligence or a computer here to make decisions. And maybe amplify the error. These are all actions that you might want to perform on the error signal before it gets fed to the engine and the car. So in this class, we are going to call this block the controller. The controller will, by and large, be the system that takes the error in and decides what to do with it. The simplest controller I can imagine is just a unity gain. That is, whatever the error is, that then gets fed into the actuator of the system. So let's talk about actuators. An actuator is kind of what the name says. It brings a desire, or it brings a command signal to actuality, to reality. An actuator takes the effort dictated by the controller and manifests it physically. So what would that be in our cruise control example? Well, the throttle in a car controls the amount of fuel that goes to the engine. So that should probably be thrown in here. Of course, the engine will take that fuel and combust it and turn it into, I don't know, torque or speed of the drive shaft, which means that we have to talk about the drivetrain, which is the general term for what happens between the wheels and the engine. That includes the gearbox, differential, all these kinds of mechanical things that as electrical engineers, you're like, whatever, let the mechanic deal with it. But these are all the actuators in our cruise control system. The drivetrain then drives the wheels. Let's see if I can erase. Hey, look at that. And the wheels are attached to the tires. And then we've come to the end of the car, basically. So from the control engineer's perspective, the actuator is just the car, pretty much. Everything you and I think of when we think of a car is there to affect the speed of the car, all right? To take the command from the controller and change it into what? What signal comes out of the tires? Well, if you think about it, the tires drive the car by exerting a force on the asphalt, yeah? So I'm going to call this signal the drive force. Yeah, we've abstracted everything inside the car between the dashboard and literally where the rubber hits the road as an actuator. And so if we just consider that as a black box, which as EEs, that's all I want to do. I tell the throttle to do something, and then the tires exert a force. That's what we're going to model here. So are we done? I mean, I've left a big blank spot in the diagram. We're not done. How is a better question. how do I get from here to there? Think about that for a second. Coming out of the actuator is a force. And if you like, units are your friend. We're not going to talk a whole lot about units in this class, but in terms of block diagrams, units are your friends. If I want to add two signals, they better have the same units. Right? I can add miles an hour with miles an hour. I can't add miles an hour with volts. So that's kind of the clue here, is that if the speed signal is miles per hour and the force signal is measured in pounds or newtons or whatever, we have to find a system, a block, that changes force to speed. Caesar, go for it.
Oh, isn't there a relationship between like the force between the tire and like the center of the tire? So that's like a torque. So
sure.
Like,
so
torque
the
is ground force, and you can kind of get like, and torque is what? It's a rotation, and you can then get rotation and maybe make some calculation to get speed or distance traveled or something like that. No?
You're on the right track, but I think that the conversion from torque to force, we've actually already covered that when we went from the drivetrain to the wheels and the wheels to the tires. So now we're just zooming in on that little rubber patch where the tire meets the road, and that we've generated a force. But think about it this way. If you are, how could you do this? If you've got an empty car and it's just you in the driver's seat and you accelerate or you press the pedal down to, say, to the floor, you're going to have some kind of acceleration. Ooh, 3 participants raised their hands. Sorry. I can't see who raised their hand because I'm sharing the screen. So go ahead and just yell at me. Or let me finish my thought. Take that same car and pile in a bunch of your friends. No, sorry, we got a social distance. Don't pile in your friends. Pile in a bunch of sandbags that can't get you sick. And if you put the pedal to the floor, you're going to have the same force but a different acceleration. What I'm getting at here is we need F equals ma. Jeremiah, is your hand up?
Yes, I thought you were going to segue into it, but I guess I might as well just ask now. When we're going through the thought process behind our block diagrams in this setup, I see we have a controller and we have our actuator. Would we have to include any more information in our block diagrams, would you think, if we needed to elaborate more on our block diagram? As in, I guess what I could say is our actuator, in this case, we could include almost everything we could think of, essentially like you meant, what you meant or spoke before, being the actual car itself. And would I have to include any more information, or do I have to describe every single technical detail that I could think of?
So the more, it's a balancing act. Actually, it's a good question, but it's not an easy one to answer. I think of these functional block diagrams as very high level concepts. The more specific you are here, the easier it will be to do the next step and the step after that in this design process. But it's also very easy to get bogged down and say, oh, well, you said engine, but you actually meant intake manifold, cylinder, piston, exhaust manifold. Okay, sorry. But I'm trying to strike a balance here between explicitly calling out the components and kind of abstracting them away. Does that answer your question?
Yes, thank you.
Sure. Okay, so we know that we can relate force to acceleration via mass, but we don't actually want acceleration, we want velocity. So maybe instead of A, I can write V prime, dv dt, if you like. And we can just note here that velocity we're going to treat as the integral of acceleration. Okay. So this is what I would call the process. So we've got the controller, we've got the actuator, we've got the process, or the thing that we are trying to control, the process that we need to modify in order to achieve our specifications. Now you notice I haven't connected the dots completely here, and that's because I also want to roll in another summing junction. Because it is at this point that we remember, oh, well, we learned F equals ma, but then shortly thereafter we learned it was the sum of the forces is mass times acceleration. So I want to call your attention to the fact that we have multiple forces acting on this car. There's the drive force, the force that we want, the force that we can control nominally, but then there's forces that are outside of our control, such as gravity going up and down hills, such as drag. That is it a headwind? Is it a tailwind? Is it gusty? Is it a crosswind? Are we driving by a semi and we're in the draft? And probably there's others you can think of that I haven't thought of, but these are all going to be forces that we can add or subtract, right? You can have a tailwind or a headwind. You can have an uphill or a downhill. So these are kind of, they could go either way. And then here, this is the net force on the car. So let me see. All right, our first color change, because it's getting a little crowded here. These are what we call disturbances. They are exogenous inputs to the system, and if we can't control them, if they don't enter into our model, it's usually best to call them a disturbance. This is to separate them from this signal over here, which is also exogenous, but it's part of our reference system. So this is what I would call the reference input. So these are disturbance inputs. You can tell they're inputs because they are arrows that don't come from anywhere, right? They just kind of appear on the page. And this is a reference input. And then this is the output of the system, all right? This is taking longer than I thought, but I think it's good. I usually gloss over this when I teach this face-to-face, so I think we're making good progress here. Questions before we move on to step number 3? Again, my screen space is limited, so if you raise your hand here, I actually can't tell. I just get a notification that people have raised their hand, so go ahead and just unmute yourself and have at it.
Hello?
Yeah, go ahead.
I was wondering if we could just once again go over exactly what the effort in this example would be.
Sure. So the controller, and I acknowledge that the controller is kind of vague at this point. I'm saying that there's some logic. I'm not telling you what that logic is. There's some amplification. I'm not telling you how much it's being amplified by. But the idea is that the controller is a subsystem that takes the error in the system and converts that into a signal that it will send to the actuator. So in our model here, the throttle is basically the first component in this actuator chain. So this would likely be an angle, or in modern cars, it would probably honestly be a voltage. We have what's called electronic throttle control. But if you want to think about it in terms of something that's maybe a little bit easier to mechanically understand, the throttle is a valve, and it takes pressurized fuel, and the smaller, or the bigger this angle becomes, the more fuel can pass through into the engine. Okay, so in this particular example, the controller takes the error that it measures between the reference and the output, and if that error is large, you could imagine that the throttle angle would be large. If that error were small, then the throttle angle might be close to neutral. Now, what you've hit on here is actually a major shortcoming of the cruise control example as your first control system. We aren't talking about brakes. We're just talking about the engine. So that is a gross simplification, but honestly, one that most cruise controls nowadays use, right? Your cruise control in your car, unless it's a pretty fancy car, doesn't touch the brake pedal. It just opens or closes the throttle to adjust your speed, and it relies on the drag to slow the car down. I didn't catch your name, which is going to make it hard to record your participation. So, new rule. If you want to ask a question, say your name first. Any other questions?
For the process, is that the part where it would actually be recording the number of spins of the tire to figure out the speed? Or is it just talking about the overall speed in this broadened viewing?
Good question. So I haven't actually talked about how to measure the speed at all. And so what a lot of people would do is they would put an extra block down here, and they would call that the sensor.
Thank you.
Yeah, of course. Anyone else? Alrighty. So let's see, can I go to the next slide? Yeah. All right, this will probably be our last topic for today. Let's transform this system, this functional block diagram, into a schematic. So this is going to be kind of a hybrid between a circuit diagram, a free body diagram, all kinds of business like that. But at the let's start at the beginning. We have the driver taking some actions, and those actions are going to be interpreted by the user interface. This could be as simple as a button on the end of one of the stalks on your steering column, or it could be as fancy as a full touch screen interface. But the important part of this, and I don't really want to model it too intricately because that's something for the software engineers to do, is the output of this is still the set speed. But the benefit of modeling this driver user interface is that it allows us to convert that set speed into a voltage, right? Whether you press the button or whether you dial it into your touch screen, at the end of the day, you have some electronics that have just translated your desired set speed into a voltage that it will then send to the controller. So let's talk about what the controller might do, or what form the controller might take. If we are going to be measuring speed in volts, and I want you to think about what I just said, and I meant what I said, we're measuring speed with volts, not with MPH, not with RPM. We are translating linear speed of the car via some translation operation to be measured in a signal with volts. So that's actually a good clue, is that the speedometer, whatever speedometer we choose to use in the car, will have to take the actual speed which is fine to be in miles per hour, and convert it into the actual speed. But now measured in volts. Okay, so that's a non-trivial operation and often gets overlooked. Because, so you buy a speedometer from company A, and it might have that 60 miles an hour corresponds to 3.4 volts. You buy a speedometer from company B, and all of a sudden it has a gain that says 60 miles an hour is 10 volts. Those two speedometers are not interchangeable unless you were to then change what comes downstream, okay? So now we've got two speeds measured in volts that we can take the difference between and do operations on that. Now here's where, this is actually where we're gonna start talking about electrical engineering. You could use any number of different circuits to do the following operation. You could use a diff amp. You could use a Darlington pair. You could use what I'm going to employ, which is going to be just a plain old op amp. I'm going to introduce an impedance network here. What is going to go into that impedance network, we don't quite know yet. Oh, and now I've entered my circuit diagram part of the schematic. This is going to be fed to the inverting terminal of an ideal op amp, because that's where we are in our EE education right now. And we're going to get a branch that comes down here, and we're going to have an impedance network down here. And yeah, okay, that's super messy. I can't abide that. Sorry. There we go. We're going to ground the non-inverting terminal, and we're going to put a ZF network here. Okay, so something very subtle but pretty important just happened. We went from kind of an abstract signal into stuff like this, which are actual wires, which carry actual current, and these are different, right? If I introduce a pickoff here, I have to remember that that's a current carrying wire, and I can't just split off the current and assume that all the other things will be equal. No, I have to account for KCL. Whereas, if I were to take this and split it off, now I'm talking about a block diagram. I can go ahead and split off that signal without changing this signal. So I'm going to come back to that point a couple times, but I want to bring it up because it is confusing. That there are some block diagram elements here, and then there are some circuit element diagrams here. Oh no, what have I done? Okay, sweet. Okay, so I want you to see that this network, this Z1, Z2, ZF, and op amp will perform filtering. It will also perform summing. It will also perform amplification, if we like. I think that what we've just done is we've modeled the controller as a summing op amp. Okay. So what signal comes out of here? I don't really have a good name for it, but it will be measured in volts. That might be passed through what's called a power amplifier. And the idea behind a power amplifier, this is fourth year stuff, but the output of your controller op amp is likely going to be medium range voltage, very low current. The power amplifier is going to take that to be high voltage, high current, okay, just so that you can drive mechanical things that themselves will draw lots of current. Okay, so we are moving right along. And that's as good as I can do in terms of the schematic for everything that I had in the actuator before. Yeah, switch to mechanical engineering if you want to know more about that block. But the idea is a voltage will come into it and a force will come out of it. Again, we could spend probably an entire quarter talking about car stuff and how to model that, but that's not this class, not this major. We can also have the net disturbance coming in here. So let's go plus and minus for these two signs. And then this would be a free body diagram for the car. So I went a little quickly over the rest of the diagram, but that's because I wanted to pull your attention to the electrical stuff, to the stuff having to do with controls, and not so much to the stuff that is not a focus of our class. All right, that brings us to 9 o'clock. So I guess we'll pick this up on Wednesday.